So I actually lugged a 50-pound Itanium 2 all the way here from Redmond, Washington. Not sure if everyone can see it. Those in the front can. Unveil that. What I've got down here is an HP box. You can come up and see it after the talk as well. I've got an HP dual processor Itanium 2 machine hiding here at the top of the stage. Now, slide decks are okay. Talk is cheap. You probably want to see whether or not this really works. And I figured nobody would believe me if I didn't actually show you the machine stats. So here it is, Itanium 2, 4 gigs of RAM. Wouldn't you all like to have this machine? 64-bit machine. All right, so let me do a very quick copy here. Quick show of hands again. How many saw the interop talk earlier today? Excellent. Well, for you folks, let me flip back ever so briefly. So Adam Nathan showed a demo. It was a console application. Showed a few lines on the screen, something you would have seen from the early 80s. And then he showed you what it would have looked like in the early 90s by adding a little color to it. So this is that same application here. Notice that it's doing platform invokes. It's got some methods actually to call out to the OS. This is what actually gives it color. Take a look very quickly here. Or not so quickly, as the case may be. So here's the 1980s application and the 1990s application. This is doing platform invoke today, and this is on a 32-bit machine. So my machine is still responding here. All I'm going to do is take that console application, copy it over to my 64-bit machine. There it is. 32-bit managed code running in a 64-bit environment with platform invoke. No extra effort. Let's switch back for a moment. So I mentioned earlier that there are some problems with transcendental functions. Now, this is something you might not care about now, but sooner or later you'll run into it. Take a look real quick. Extremely simple piece of code. All I'm doing is taking a single precision floating point number, and I'm taking sign of that. You notice this is a huge number. 1e to the 38th is just at the border of precision. Double precision float, I'm doing the same thing. 1e to the 308th, taking sign of that number. Okay, does that look correct? What you find out, and I could have reformatted the first one. Basically, the first one is also 1e to the 38th. What actually happens on x86 is at the edge of resolution, it says, I give up, I'll just return you the number. And when you think about it, in some ways, that's respectable. If you can't give the right answer, give one that's hugely wrong. If it's outside the range, I mean, you're looking for -1 to 1, right? You can write a really easy test that says, if I'm greater than that number, and this clearly is greater, but it's certainly not what you expected. Again, copy that one over. Hey, we get back what we expected. Exactly the same code. I didn't rebuild. I just copied this neutral application over. Different behavior in the outcome. So again, something to take a look at. You really need to take a look at the Intel documentation on this to find out how this happens. The standard is going to tell you, if you look at the IEEE standard, it'll tell you what's indeterminate. It won't tell you, obviously, the outcomes on various chips. If you care about doing math like this, take a look at the documentation. All right. A couple more extremely simple ones here. I decided to do the same thing. We talked about managed C++ applications. Now, I thought that output was really strange on x86. That was with the C# app. So I decided to do the same thing with C++. Make sure. OK. Here we're getting the same result that we got from our C# application, right? So I decided I want to see what that one looks like on the 64-bit machine to make sure we're seeing the same thing. Oh, that's a problem. Everybody know what happened here? So this one's kind of a trick question. So the managed C++ application, despite the fact that I only made managed calls, that's tagged as a 32-bit executable. I brought that one across. There's no 32-bit runtime over here right now. This is a fairly cryptic error that says, hey, I don't even know how to start up the image. Proof that these things are actually 32-bit. Chances are good you will never run into this. We plan on shipping the 32-bit and the 64-bit runtimes together. It would be very, very difficult for you to get one without the other on your 64-bit machine. But what you do need to watch out for is the fact that I ran the C# app, it executed as a 64-bit image. I run the C++ app that ostensibly does exactly the same thing. It's going to start up as a 32-bit image. Might mean something to you. Something else that I only briefly mentioned, let's actually go to the bottom here, or partway in between. So you see some of the assemblies we recognize. System design. You're seeing the four-part names of these assemblies. We have the name of the module, version, culture, public key token. Now, if you're used to strong naming your assemblies, these are things that you see today. This is all on the x86 platform. Taking a look on IA, let's see here. Notice now you actually have that processor architecture. Can everyone see that okay? So now the global assembly cache actually does know about IA. It knows about AMD. It'll do smart things like it won't allow you to put a binary into the GAC for an architecture that does not make sense. And obviously, this one here says that it's processor architecture IA64. This one is bit specific, 64-bit specific. This one is neutral. So that's what I mentioned before, that all of the stuff we're trying to generate to be portable is actually tagged as neutral code. Lives in a different area of the global assembly cache. I don't actually have any here that are 32-bit specific, but you would see those as well. And then there's that other section of the GAC called legacy. Let me show you that very quickly. So I have a VB app that I wrote. This little thing here we call VB64, very simple app. All it does is shows a little form. The app itself isn't that interesting. What I really wanted you to see is that now ILDASM, if you can see the bottom of the screen, ILDASM actually reports this as a legacy assembly. So the things that you're writing today with RTM Visual Studio or Everett Visual Studio will actually show up as legacy components that don't know anything about newer components. All right. Just about at demo exhaustion. Show one more thing real quick. I'm an avid chess player. Other chess players in here? Okay. So I always have this canonical application as I go from language to language and architecture to architecture. Now, this is a small room, so I'm going to admit this, but I originally wrote this in Java years ago. So when I moved to the CLR team, the first thing I did was begin rewriting it in C#. So this is actually several assemblies. There's an assembly here, a DLL, that knows the format of saved games. So if I want to, I can actually just open up games that I've got saved. Because I like to step through the games of people who actually know what they're doing. In this case, this is a game from 1886 from the world champion. And I can then step through, play the game, find out whether or not he won or lost. So I've got that assembly that reads the files. I've got assemblies that understand how moves can be made, what's illegal, what's legal. And of course, I've got the Windows form that shows off the UI. So it's a little bit bigger than the other applications that I've shown you. Ever so slightly slow over here. There we go. A rather large WinForms application. This is a bug, by the way. Let me show you one of those. It's a current WinForms bug. Oh, I guess I didn't copy the game over. But you see, essentially, it's the same thing. It knows how to do the moves, knows what's legal and what's not. So there you go, a large WinForms application. I did no recompile. I copied all of that over. Actually, all of these assemblies are strongly named. So if you take a look at everything there, you see a number of DLLs. I can install that assembly to the GAC. There we go. Notice it's not tagged processor neutral. Anybody guess why that is? This is a legacy component. So those APIs to actually tag your executables, those don't come along until WDBI. So things before that are considered legacy, and legacy is essentially neutral. That's why you're not seeing it here. But there it is. Oh, let's start one more of those back up. One last thing. How many of you are actually down deep debugging folks? How many people step through disassembly? Anybody? Okay. So there's one person in the back that's gonna appreciate this. The one thing I wanted to show is that the Visual Studio Debugger is a wonderful thing. It's hugely powerful. There are instances, however, when you get past what it's capable of doing. Wanted to show you a little known tool. Whoops. WinDBG. How many folks have seen this? Excellent. Okay. So you folks who said you didn't step through disassembly, what are you doing in WinDBG? Wow. Okay. There you go. So starting up the application. I think it should be there by now. Yep. All right. Breaking in the debugger. I know that the managed thread is the first thread, so I'm just skipping to that. So those of you who've used WinDBG, how many of you know about SOS? Anybody seen that? Oh, okay. This is the thing I wanted to show you. A set of debugging extensions that really make using WinDBG worthwhile. So it's implemented as a DLL that's loaded as an extension. Number of impressive things that it can do. It can actually, from unmanaged code, dump the state of all of the managed objects that are executing. So it can dump classes, dump what's in an app domain, dump heap space, translate from an instruction pointer back to the method desk of a managed object. Hugely important if you're trying to do debugging between managed and unmanaged. So let me see if I can get it to do something smart real quick here. All right. So SOS stands for Son of Strike, by the way, which is what you see up there. So what I did is I just dumped the CLR stack, the managed stack. And you see Windows Forms application run, all the things you'd expect from a WinForms app. I'm going to do one other thing that I consider a minor miracle. Let's see if that works. There we go. So if you notice up here in the command window, a little bizarre, EIP, I actually have the instruction pointer for each one of those methods. I just told Son of Strike to change that IP into a managed method desk. So it tells me everything about this method. It says it was JITted by our pre-JIT. That tells you it's probably from a system assembly, that it was generated with NGen beforehand. Method name, the table, the module. From here, I can work backwards as far as I want into the unmanaged portion of the CLR. So, okay, enough of that. I can fortunately do the same thing here. And while this is boring and repetitious, it's here to serve one purpose. So in the command window already, you notice how much wider everything is? First couple of columns are addresses. Look at the size of that. I have lots of memory in this machine, so. commands are ever so slightly different here. But we're getting the same information. Notice that, let me make this a little larger. Notice that we're getting system Windows forms. Here's my main function from my VB app. Oh, load SOS again. And here's my disassembly of that same function. Don't worry about the unassembly not yet implemented, little placeholder. Hugely different from x86. That huge number of registers I mentioned, floating point registers, and all of your standard registers. What's that? What is this, 30? I can't remember the number of general registers. Is it 30 some? I don't remember off the top of my head. We could count them real quick. It is in the, no. I'm wrong. The number of general registers is clearly much higher than that. It looks like 128 general registers. All right. So that's all I wanted to show there. Befuddle you with the size of everything IA64.